Good morning. Myself, Mr. Dibyendu Mondal, Assistant Professor of Greater Kolkata College of Engineering and Management under JIS Group. So, this is my lecture number 7 of Module 1, and class, it is the class of Solid Mechanics. Today, I am discussing about analysis of bars of varying sections. Okay, analysis of bars of varying sections. Okay, now let's start. Analysis of bars of varying sections. Now, a bar of different length and different diameter, different cross-sectional areas shown here. First one is the area A1, second one is the area A2, and third one is the area A3. And another one is the length is equal to L1, L2 and L3. There are three length. One is the L1, another one is the L2, another one is the L3. Though each section is subjected to the same axial load P, yet the stresses, strains and change in length will be different. The total length, change in the length will be obtained by adding the changes in length of individual sections. First one is the P is equal to axial load acting on the bar. L1 is the length of the section 1 and capital A1 is the cross-sectional area of section 1. L2 and A2, that is the length and cross-sectional area of section 2. Another one is the L3 and A3, length of the cross-sectional area of section 3. And capital E, that is the Young's modulus of the bar. Then the stress for the section 1, sigma 1 is equal to load divided by cross-sectional area. So that is equal to P by A1. Now, stresses for the section 2, that is equal to P by A3, sigma 2, P by A2, that is equal to sigma 3 is equal to P by A3. So, using the equation strain of a section 1, that is equal to E1 is equal to sigma 1 by E. So, that is equal to P by A1E. Now, the total elongation, the strain of section 2 and section 3 are E2 is equal to sigma 2 by E, that is equal to P by A2E, and E3 is equal to sigma 3 by E, that is equal to P by A3E. But strain in section 1, that is the change in length of section 1 divided by length of section 1. So E1 is equal to dL1 by L1, where dL1, change in length of section 1, change in length of section 1 dL1, that is equal to E1 L1. Similarly, change in length of section 2 and section 3 are obtained as change in length of section 2, that is the dL2, that is equal to E2 and L2. So that is equal to PL2 divided by A2E. And change in length of section 3, that is equal to dL3, that is equal to E3L3. So therefore, the total change in the length of the bar, that is equal to dL is equal to dL1 plus dL2 plus dL3. So PL1 divided by A1E plus PL2 divided by A2E plus PL3 divided by A3E. So that is equal to P by E, L1 by A1 plus L2 by A2 plus L3 by A3. So the equation is used when the Young's modulus of different section is same. If the Young's modulus of different section is different, then the total change in length of the bar is given by dl is equal to p into L1 by E1 A1 E1 plus L2 by A2 E2 plus L3 by A3 E3. Here the one problem, an axial pull of 35,000 Newton is acting on a bar consisting of 3 lengths shown here. If the Young's modulus equal to 2.1 into 10 to the power 5, determine the stresses in each section and total extension of the bar. So this is the 35,000 section 1 2 centimeter diameter, 3 centimeter diameter, and another one is the 35,000 Newton, 5 centimeter diameter. Axial pull is equal to 35,000 Newton. Length of the section 1, that is equal to L1, that is equal to 20 centimeter or 200 millimeter. Diameter of section 1 D1 is equal to 2 centimeter, that is equal to 20 millimeter. Area of section 1, that is equal to A1, that is equal to pi by 4 into 20 square, that is equal to 100 into pi millimeter square. Therefore, length of the section 2 L2 is equal to 25 millimeter, that is equal to, after calculation you get 250 millimeter. Diameter of section 2, that is D2, that is 3 centimeter, 30 millimeter. Now your objective is stresses in each section. Stress, first one area, first one you calculate. When you calculate when you solve the numerical problem related to stress strain, first one you calculate the area. Stress in section 1, that is equal to sigma 1, that is equal to axial load by area of the section 1. Axial load 35,000 divided by A1, that is equal to 100 pi. Okay, so that is equal to 100 pi. The axial load 35,000 divided by 100 pi, 111.408 Newton per millimeter square. Stress in section 2, sigma 2, that is equal to P by A2, 35,000 divided by 225 into pi. So that is equal to 49.5146 Newton per millimeter square. Stress in section 3, that is equal to P by A3. So after calculation, 35,000 divided by 625 pi. So that is equal to 17.825 Newton per millimeter square. Therefore, the total extension of the bar, that is equal to capital P by E, L1 by A1 plus L2 by A2 plus L3 by A3. 35,000 divided by 2.1 into 10 to the power 5, 200 divided by 100 pi plus 250 divided by 225 into pi, 220 divided by 625 into pi. So that is equal to 35000 divided by 2.1 into 10 to the power 5 plus, after calculation, 200 by 100, 200 plus 100 by 100 pi. So that is equal to 6.366 plus 250 divided by 225 pi, that is equal to 3.536. 220 divided by 625 into 625 pi, so that is equal to 1.120. Okay, that is equal to 0.183 millimeter. Okay, so therefore total extension P by E, that is equal to L1 by A1 plus L2 by A2 plus L3 by A3. 35,000 divided by 2.1 into 10 to the power 5, 200 divided by 100 pi plus 250 divided by 225 into pi plus 220 divided by 625 into pi. 3500 divided by 2.1 into 10 to the power 5. So 6.366 plus 3.536 plus 1.120, that is equal to 0.183 millimeter. Okay. Now second problem. First one, you read the problem carefully and then you solve. A member formed by connecting a steel bar to an aluminium bar is shown in figure 1.7. Assuming that the bars are prevented from buckling sideways, calculate the magnitude of force P that will cause the total length of the member to decrease 0.25 millimeter. The values of elastic modulus for steel and aluminium are 2.1 into 10 to the power 5 Newton per millimeter square and 7 into 10 to the power 4 Newton per millimeter square respectively. So first one, look at the figure. This is the figure. Cross sectional area 5 centimeter into 5 centimeter, steel bar 30 centimeter. Another one is the 10 centimeter into 10 centimeter aluminium bar. Area of the steel bar, that is equal to A1, that is equal to 5 into 5, 25 centimeter square. So that is equal to 250 millimeter square. Elastic modulus for the steel bar E1 is equal to 2.1 into 10 to the power 5 Newton per millimeter square. Okay, and length of the aluminium bar L2, that is equal to 38 centimeter, so 380 millimeter. Area of aluminium bar A2 is equal to 10 into 10, so that is equal to 100 centimeter square. So that is equal to 10,000 millimeter square. Elastic modulus for aluminium bar, that is equal to E2 is equal to 7 into 10 to the power 4 Newton per millimeter square. So total decrease in length DL is equal to 0.25 millimeter. So let P is the required force. As both the bars are made of different materials, hence the total change in the length of the bar is given by DL. So DL is equal to P into L1 by E1A1 L2 divided by E2A2. So 0.25, that is the total elongation given in the numerical problem, 0.25 P into 300 divided by 2.1 into 10 to the power 5 into 2500, 380 divided by 7 into 10 to the power 4 10,000. So that is equal to P into 5.714 into 10 to the power minus 7, 5.428 into 10 to the power minus 7. That is equal to P into 11.142 into 10 to the power minus 7. So P, after calculating, P is equal to P is equal to 0.25 into 11.142 into 10 to the power minus 7. Okay, that is equal to 11. Actually, after calculating, you get 2.2437 into 10 to the power 5. So that is equal to 224.37 kilonewton. 224.37 kilonewton. The bar shown in figure subjected to a tensile load of 160 kilonewton. If the stress in the middle portion is limited 150 Newton per millimeter square, determine the diameter of the middle portion. Find also the length of the middle portion if the total elongation of the bar is to be 0.2 millimeter. Young's modulus is given as equal to 2.1 into 10 to the power 5 Newton per millimeter square. So tensile load, that is equal to P 160 kilonewton, 160 into 10 cube Newton, and total elongation sigma 2 is equal to 150 Newton per millimeter square. So total elongation is dl is equal to 0.2 millimeter. Total length of the bar L is equal to 40 centimeter, that is equal to 400 millimeter. Capital E, that is equal to, so therefore the first one, tensile load, that is equal to P is equal to this one, 160 kilonewton into 160 into 10 cube Newton. Stress in the middle portion sigma 2 is equal to 150 Newton per millimeter square. Total elongation, that is equal to 0.2 millimeter, and total length of the bar, that is equal to L is equal to 40 centimeter, that is equal to 400 millimeter. Young's modulus, capital E, that is equal to 2.1 into 10 to the power 5 Newton per millimeter square. So diameter of the both end portion, capital D1, that is equal to 6 centimeter, 60 millimeter. Area of the cross section of both end portion A1 is equal to pi by 4 into 60 square, that is equal to 900 pi millimeter square. Now D2, diameter of the middle portion, and L2 is the length of the middle portion. Length of both end portion of the bar L1 is equal to 400 minus L2 millimeter, and using the equation stress is equal to load by area, for the middle portion we have sigma 2 is equal to P by A2. তাহলে sigma 2 হচ্ছে 150 by 160 000 divided by pi by 4 into d square. D2 square, that is equal to 4 into this 160 into 000 divided by pi into 50, 150, 1358 millimeter square. Okay, so D2 is equal to root over of 1358, so that is equal to 36.85 millimeter, so 3.685 millimeter centimeter. Area of the cross section of the middle portion A3 is equal to pi by 4 into 36.85, so that is equal to 1066 millimeter square. Now using the equation total extension dl is equal to P by E L1 by A1 plus L2 by A2, 0.2 1600 divided by 2.1 into 10 to the power 5, 400 minus L2 divided by 900 pi plus L2 1066. So after calculating 0.22.1 into 10 to the power 5 by 16000, 400 minus L2 divided by 900 pi, so plus L2 by 1066, so that is equal to 0.2625 into 900 pi into 1066, that is equal to 1066. After calculating 1066 L2 plus 2827 L2, so L2 is equal to, after calculating 364786 1761 that is equal to 207.14 millimeter. So if you convert into centimeter, that is equal to 20.714 centimeter. Okay, thank you. So my lecture video is uploaded in YouTube. If you like it, you have to subscribe my channel. And if you face any problem, you may contact anytime through mail or over telephone. Okay, thank you.